So this lesson is all about what we call the greatest common factor, or for short, GCF. And to understand what the greatest common factor is, we just actually have to look at the words that make up the term greatest common factor. And we'll do it in reverse order. The F, of course, standing for factor, that's something that we're familiar with. We saw it in the last few lessons. You saw it in previous years. No surprise there. The C, standing for common factor, means that they're going to be factors that several numbers have in common. In order for things to be common, we have to have more than one thing to compare to. I can't have something in common with myself. I can have something in common with my sibling. I can have something in common with a friend. I can have something in common with someone I've never met. But the important thing is there has to be at least one more person or one more object, if we're talking about comparing objects, in order for things to be common. So every set of numbers, if we have 2 numbers, 3 numbers, 4 numbers, we put them together, there's going to be some collection of factors those numbers have in common. It may be very small. It may be only one factor. It may be very large. But there's a selection of common factors. And because there are a group of factors that 2 numbers have in common, we can choose the greatest of them. And so there are 2 important definitions that I'd like you to write down. The first has to do with what a common factor is. That's something we saw before. And then, of course, the definition for greatest common factor. Go ahead, pause the video, write those down, as well as the abbreviation GCF, and come back when you're ready to see a few different ways of talking about and finding the greatest common factor. So one of the ways that would immediately come to mind about how we could determine what the greatest common factor between, let's start with 2 numbers is just by listing out all of their factors and finding which ones happen to be the greatest that they have in common. So if we wanted to list out the factors of 24 and 20, well, 24 has 1, 24, 2, 12, 3, 8, 4, and 6. I always like to think of factors in pairs because when you divide a number by a factor, you get another factor. And then for 20, 1, 20, 2, 10, 4, and 5. So if we can actually list out all of the common factors of numbers, which depending on how large the numbers are, we may or may not be able to do, then we can just look and compare and see what the greatest common factor is, which in this case is 4. Let's take a look at another example of that. For the numbers 36 and 60, however, it might be difficult to come up with all of the factors for 36 and 60. And because 36 has several factors, it has 9 in fact, and 60 actually has 12 different factors that we could find, it is entirely possible, and in fact it could be entirely likely that you miss some of the factors while listing them. And in order to avoid that, we go back to something that we looked at last lesson, and that is prime factorizations. And here's the piece of prime factorizations that is really important. Let's take a look at the number 24. Our prime factorization was 2 times 2 times 2 times 3. And I wrote that out like that intentionally, not with the exponents because we need to see all 3 2's. And all the factors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. And what I want you to notice about the prime factorization and these factors is that every single factor of 24 is actually a piece of the prime factorization. 1, we just sort of have to take for faith. We can say this is 2 times 2 times 2 times 3 times 1. And so 1 is a factor of everything. 24, of course, is a factor of 24 because we just take that whole collection of primes. But every single other factor of 24 is in the prime factorization somewhere. 2, for example, is just one of those 2's. 3, for example, is just the 3. You take 2 of those 2's together, you get 4. You take 3 of those 2's together, you get 8. You take the 2 and the 3 and not anything else, you get 6. Add one more 2. 2 times 2 times 3, there's 12. The prime factorization contains every single factor of that number. And if the prime factorization contains every factor, if every factor of a number can be found as a piece of its prime factorization, then if we know the prime factorizations of 2 numbers, we can just compare those prime factorizations, find every common prime that we have, and not only can we find all of their common factors by collecting all of the common primes, the things that they have that are the same. If we put all of them together, we create the greatest possible common factor. Because a factor is a piece of a prime factorization. So if two prime factorizations are there, the stuff from both that's the same, that's going to be the greatest possible combination of common primes, which creates the greatest possible common factor. Go ahead, pause the video, write down these two important things, and then come back to see an example of how this works in process. So let's take a look at one of those things we've already done. 24 and 20. We know, because we listed their factors, their GCF is 4. Let's use that to our advantage. We know that the prime factorization of 24, as we saw before, is 2 cubed times 3. 20, we can find out from the factor tree, is 2 squared times 5. I'm going to trust that you can find that factor tree, so I'm actually not going to write it out here. And now we're going to take these two prime factorizations and we're going to look at them and say, well, what stuff is the same in both of them? Certainly not a 3. A 3 isn't the same because 20 doesn't have a 3 in its prime factorization, and certainly not a 5 because 24 doesn't have a 5 in its prime factorization. But they both have 2's. 24 has 3 and 20 has 2. And so if we're looking for all the stuff that's the same, you can't share something you don't have. So all the stuff that's the same is the smallest number of 2's. They both have 2 2's. And if we multiply out 2 to the second power, guess what we get? The GCF, which is 4. Let's take a look at that with 36 and 60 now, or rather with 50 and 20, and then we'll look at 36 and 60, and find out what those GCFs are. 50's prime factorization is 2 times 5 squared. 20, as we said, is 2 squared times 5. So if we're looking for all the primes that's the same, we have to look not only which primes do we see in both numbers, in which case, in this case, both the 2 and the 5 show up in both numbers, but we also have to look at how many primes how many copies of those are the same between both. And they can only share as many as the smallest number that they have. So they can only have 1 2 that's the same. Even though 20 has 2, 50 doesn't have 2, and you can't share something you don't have. Similarly, a 5 is common, but only 1 5, because 20 only has 1 of them. And putting those two common primes together, 2 times 5, that gives us the GCF, which is 10. Let's take a look at that with 36 and 60, because that was something that we saw before. 36, after we use our factor trees to find everything, is 2 squared times 3 squared. 60 is 2 squared times 3 times 5. So what are their greatest common factors? Well, they each have 2 2's. That means 2 2's are the common number that they have. It's the smallest number of any of them. We also have some 3's that they have in common. Both of them have 3's, but 60 only has 1 of them. 36 has 2, 60 only has 1, so they can only share the smallest number that they have, and then 36 doesn't have a 5, so we don't have to worry about the 5 for 60. We put all those common primes together, the smallest number of all the primes that are the same, and we get their greatest common factor, which is 12. So go ahead. So when we do this with greatest common factors and we find the prime factorizations, we look for all the primes that are the same, and we pick the smallest number of those primes because you can only share what you have. So in this case, 36 may have 2 3's, but they can only share 1 of them because 60 only has 1. So a single 3, is a part of the greatest common factor. So go ahead, pause the video. We're going to do 2 pages worth of example problems here. Use factor trees to find the prime factorizations, find all the primes that are the same, and use those to find the greatest common factor. Pause the video, work on these, come back when you're ready to see the answers and move on. So for 45 and 24, 45 as a prime factorization, you should have gotten 3 squared times 5. And 24 is 2 cubed times 3. So the only prime that they have in common is a 3. 45 has 2 of them. 24 has 1. They can only share the lowest number that we see, so the greatest common factor is 3. For 13 and 52, 13 is, well, prime, so its prime factorization is just itself. 52 is 2 squared times 13. Now, if we're looking for the primes that they have in common, the only one they have in common is a 13. There's only one 13 in each of them, so they can only share one. That one 13 is the only one that's the same in both. So the greatest common factor happens to be one of the numbers in this case. It's totally possible, 13, because 13 is a factor of 52. 2 more problems here. Go ahead, pause the video, find the GCF by finding the factor trees, finding all the primes that are the same between the two, and then using those to calculate out the GCF. Pause the video, come back when you're ready to see the answers, and then see one last thing. So for 120, we have 2 cubed times 3 times 5. And for 95, we have 5 times 19 as our prime factorizations. Now, the only prime that we see that's the same between them is a 5. And, in fact, the number of 5s in each is the same, which is 1. So the GCF is 5. Notice I'm not taking copies of it from both numbers, because then we have 2 5s. Neither of the numbers have 2 5s, so 5 squared cannot possibly be a part of the greatest common factor. And then for 25, speaking of 5 squared, we have 5 squared, and 24 is 2 cubed times 3. Now, you may look at this and first and say, wait a second, there are no numbers that they have in common. And that's true. There are no prime numbers in the prime factorizations of 25 and 24 that are even remotely similar. 2s, 3s, and 5s in different combinations, but nothing that's the same. But there is one factor of every number that is always the same, because 25 and 24 are special pairs of numbers. Their GCF is 1. They don't share any primes, but 1 divides into every number, so 1 is actually a factor of every number. And 2 numbers, or more than 2 numbers, whose GCF is 1, we call those numbers relatively prime. So go ahead, pause the video, write down this definition here, somewhere near where you did the work for 25 and 24, because those are examples of relatively prime numbers. Come back when you've written that down for a quick review of finding the GCF with prime factorizations. So remember that GCF stands for greatest common factor. We're not looking for just any common factor, but we're looking for the greatest of the factors that 2 numbers have in common. And instead of listing out those factors, which is imprecise and is prone to forgetting some, we actually use the prime factorizations, because all of the factors of a number can be found inside the prime factorizations. If we find all the primes that both numbers have, and we find the number that's the same between both of them, which is always the smallest number of each of those primes, take all of those common primes together, put them together, multiply them out, and you get your greatest common